Yes, ma'am.
Yes, ma'am.
Okay. So yeah, in the last class we had discussed about the complexity analysis of the searching algorithms. Now we move on to the complexity analysis of the sorting algorithms. So we'll discuss the time complexity of each algorithm one by one, and since all these algorithms you have already studied in your last class, so I'm not going to get into the details, deep details of all these algorithms. So I told you in the last class that you have to revise your concepts of the sorting technique. So you will be telling me what is a particular sorting technique. Okay. So first of all, tell me what is selection sort. Who will speak up? Selection sort.
मैम हर पास में हम लोग मिनिमम एलिमेंट ढूंढते हैं. मतलब we take the minimum element or maximum element and put it in place.
Let us do that. When we are sorting it in the ascending order only. So you answer accordingly, right? So what do we do in the selection sort?
We first select a particular, we select an index and then choose an element for that index, the shortest, the smallest element. For example, first we'll choose the with index and then the smallest element.
Okay. So now we are going to discuss the complexity of the sorting algorithm. So just a review that in the selection sort, we sort the array by repeatedly finding the minimum element, as you said, right, from the unsorted part and put it in the at the beginning. So that means when we are using the selection sort algorithm, we have basically we have to imagine that the array is divided into two parts. One part is totally sorted part and another part is the totally unsorted part. So the you can say the subarray one you can say the front part, because we are what we are doing, we are picking the minimum element and putting it in the front. So the front part of the array we can say that is always sorted part, and the later part is always the unsorted part. So in every iteration we pick up the minimum element and from the unsorted subarray, and then we move it to the sorted part of the array. So this is how the selection sort algorithm works. So you can see the your pseudocode for the selection sort algorithm, that we start with the what we have to do. We have to pick up one from the last. So that means first of all we have to find out the minimum element from the array. So for that what we are doing, we are using one loop for I is equal to 0, I less than n minus 1, I plus plus, and we find out the minimum element from the unsorted array. So this is the number of comparisons which are required. So you can say within that we are comparing all the numbers to find out the minimum. And once we have found the minimum, what do? We compare that with the first element of that particular array. Here you can say we have called the swap function, and in the swap function what we are passing two parameters. One is the index value of the minimum number, and the second one is the first you can say. So we pick up the value from the minimum value, and second one is the index of the, or you can say the first array, and then we are just swapping them using the swapping function. Swapping function is simple, as you always do. So when we are doing this particular task, here we can see we are using the two for loops and two nested loops with no break statements, right? So it is not going to break at any point of time. So the outer loop, it runs n minus 1 times. We can see I is equal to 0 to n minus 1. And the inner loop, how it is working? So in the first run of the outer loop, inner loop runs n minus 1 times. Similarly, n minus 2, n minus 3, and up to it goes to 1. So when we see this becomes a pattern from 1, 2, 3 up to n minus 1, n minus 2, n minus 3. And this is equivalent to n into n minus 1, which gives us O(n) square. So the total time complexity of this selection sort algorithm, it comes out to be in all the cases is worst, best, average. In all the cases it comes out to be O(n) square, right? So in the selection sort algorithm, we don't have any you can change in the minimum, you can say the upper bound, the lower bound, and the average, they are all same in case of the selection sort algorithm. Next, we move on to the bubble sort. What is bubble sort? Yes. What is bubble sort algorithm?
Ma'am, we keep swapping the adjacent element. In each iteration, the biggest number reaches the last of the array, and
Hmm.
in each step, we will place the biggest element to the rightmost side, thus the array is sorted.
Yes. So that means in every you can say in the first step, number of you can say there is a swapping is happening between the two consecutive positions, right? So the swapping is happening between the two consecutive positions. If like when see, I told in the very beginning we are talking. I'll be discussing from the increasing order point of view. Sorting we are doing in the ascending order. So that means if the first and the second number, first number which we are having in the array, it is greater than the second number, then the swapping will be done, right? So similarly, we keep on doing this particular process. This is called as the bubble sort. So in the bubble sort, see here you can see the arrays as it happened in the selection sort. We had one part of the array is sorted and another part as of the array is unsorted. We have nothing like that over here. So we call it bubble because some number is bubbling, moving from one position to another over the passes. So here you can see our outer loop, for loop, it is executed n minus 1 time, and we are using one flag over here which says that the flag is equal to false, and in the bubble sort the array will be you can say at some point of time we have a break statement. So that means it can come out of that loop and it can break. When it will be break? So when the swapped is equal to false. When it happens that the swapping is false? Yes. When in what cases the swapping will remain the false? The flag will remain false.
Ma'am, when the next element, ma'am, which is right to the element, is greater than it.
So that means you can say in the best case when the array is fully sorted, there won't be any swapping.
Yes, ma'am.
We can say that,
Yes, ma'am.
right? So in that case, we can say that the swapping will remain fast and it can break the loop. If two elements they were swapped by the inner loop, then it will break. So in the outer loop, then the inner loop is also being executed n minus 1 times, and if array j, that means we are just comparing the values of the two consecutive positions. Here you can see array j is greater than array value j plus 1. So j and j plus 1, they are indicated that we are comparing the adjacent values, and if the value is greater, that means if the value at index 1 is greater than the value at the index position 2, then they will be swapped, interchanged. So when the swapping happens, we say swapped is equal to true, and it will keep on iterating. And after that, we see if the swapped is equal to false, that means there has been no change over there. So it will break the outer loop. So in this particular algorithm, we say the worst and the average case time complexity is of the order of n square, because this will happen when the array is totally reversed. That means we wanted to arrange it in the ascending order, but the array is there in the descending order. And in the best case time complexity is on, it occurs when the array is already sorted. Thus, for the nested loop breaks when the array is already sorted. That's what I said, because when there will be nothing that will happen, that means the array will not be executed. So it will break this particular loop. So in the bubble sort algorithm, we say, see in the selection sort, you can say at some point of time, you can say the bubble sort is performing better than that of the selection sort, because in the selection sort are all the time complexities were O(n) square. But in case of the bubble sort, we have worst and the average case time complexity O(n) square, whereas the best case time complexity is of the order of O(n). So in that case, in the best case, you may your bubble sort is better as compared to the selection sort. Next we have insertion sort. So what do we do in the insertion sort? So what is the difference between the insertion sort and the selection sort?
Ma'am,
Ma'am,
in insertion sort,
Hmm.
ma'am, the elements are sorted toward left.
Hmm.
Every element uh, which is in the array has been sorted towards the left of it. Means every element to the left of it will be lesser than it.
Can you elaborate once again?
Means if we have an array, then we will point to the first index and
Hmm.
we'll see if it is sorted toward its right. Like if there is 2 and next is 1, then we will swap the element and see that if there is no bigger element to the left of it.
Right. Right. Who else can? Just a second. So in the insertion sort, what do we do? See, we already know the concept of the insertion sort. So the array is virtually divided into the sorted and the unsorted part. See, in the insertion sort, we basically in the selection sort we were picking up the minimum value and placing it in the front, and in the insertion sort we pick every number, we pick any number and then we check what is the appropriate position for that. So and then we place it in the appropriate position. So we are inserting that into the appropriate position. In the selection we pick up the minimum and place it in the front, right? So in the insertion sort, here you see the code for that. So the first loop, the outer loop, that is being executed n times, and we take the key. That means we pick up the element and we just want to place it in the right position. And for placing it in the right position, we see what do we do? We are just taking the element and then we start placing it in the appropriate position. Here you can see we have started another loop, that is that begins with j is equal to I minus 1. So by the time j is greater than equal to 0 and the value of j is greater than equal to key, right? So you can say when we are trying to find out what is the best position for that, so the value it is greater than, right, then array j plus 1 is equal to array of j. That means we are just trying to put the minimum, you can say you can say the uh, in the increasing order, so the interchange will take place accordingly. And then the array is equal to key. So we are just shifting the positions and then we are placing them into the appropriate position. So we are calling it as the insertion. So this way the loop will carry on till all the numbers are in their appropriate position. So here you can say for the outer loop it is being run executed n minus 1 time always. While loop inside the for loop runs differently. Here you can say in the best case while loop doesn't run at all. It may be all the elements are less than equal to key. So that means only one comparison statement is being executed. In the worst case, while loop runs one times in the first pass for loop, two times in the second pass, three times in the third pass, and n minus one times in the last pass for the loop. So in the best case, we can say its complexity of the insertion sort is of O(n) because only one comparison. That means n number of elements are there, so n comparisons are being made. So because only the outer loop is being executed, so it is of the order of n. And in the average and the worst case complexity of the insertion sort is of the order of O(n) square. That means we can say at max the outer loop as well as the inner loop, they are being executed n and n times. So we are able to get here you can see the best case time complexity of the insertion sort is of the order n, and the average and the worst case complexity of insertion sort is O(n) square, which is same as the bubble sort, right? So we can say that for the bubble sort as well as the insertion sort, their best case as well as the average and worst case time complexities are same. So next we move on to, so there are various algorithms that we have studied sorting, that is selection, you can selection sort, bubble sort, and your insertion sort. So all these algorithms, basically they are giving us a time complexity of worst case time complexity of the order of O(n) square, which is very high. So, and then we have another category of algorithms which provide better solutions to the sorting problems as compared to the previous algorithms that we have studied. So for the higher values of n, we need to have certain algorithms whose time complexity is less. And these algorithms are known as divide and conquer based sorting techniques. So as we already discussed in the beginning during the asymptotic analysis also, that in the divide and conquer techniques, the problem is divided into half at every stage. So basically, whether the problem is divided into two equal halves or they are of unequal size. Depending upon that, we have different types of divide and conquer sorting techniques. So divide the problem into sub-problems, we will say that the size of the sub-problem may be equal or unequal, and then the same process is repeated recursively. So you can say these divide and conquer algorithms, they are basically the recursive algorithms also. So now we are going to discuss these divide and conquer based sorting techniques one by one. The first divide and conquer based sorting algorithm is the merge sort. This algorithm we already discussed also. So basically it is based on the principle of divide and conquer algorithm technique. So what happens is it repeatedly breaks down the array into several sub arrays till we are able to get the unit element in the array. So that means if there are 10 elements, we will break them into 5, then 4, then you can say. So first we will break them into 5, 5, and then we are going to break them into 2 equal halves, and then finally till the size of the array is 1. That means there is only single element. And then we start integrating them one by one. That means we first divide, then we conquer, and then we merge them. So during the merging, we are comparing the elements. Like we have two arrays, one is having the element 2, another is having the element 5. So when we are combining them, they will be placed in the order 2 and 5. Otherwise, let us say if the array 1 is having the number 5 and the another array is having number 1. So the 1 is smaller than number 5. So the 1 will be placed first and the 5 will be placed next when we are merging them. So merging happens from bottom to top. So as we move from bottom to top, all the during the merging process, you can say all the elements are placed in uh, uh, all the elements, they are merged together and the sorting is being performed. And finally we get when the complete sorting is being performed from, see, when we are dividing, so we are dividing the element of we're dividing the whole array into sub problems, and finally from the during the merging we are integrating them, we are combining all the sub problems into a single problem, that is the final sorted array. So these are the steps that which are involved when we are performing the merge sort. So accordingly, we have different functions for that when we are applying the merge sort algorithm. So here you can say what is the input, a sequence of n numbers which are stored in the array A, and the output is the sorted sequence of n numbers. Here there's a misprint that the L points first element index of the array, it is basically P. So you can just note down that in the code here P points first element index of the array and R points to the last index element of the array. So that means in the merge we have A is the input sequence of array, P is the smallest element, and R refers to the last element of the array. So what do we do? If P is less than R, because we are taking the P to be the first index element of the array, so it is going to be small. So while if P is less than R, what do? We just divide, right? So we just divide the complete array into two equal halves. We are dividing it by 2. So P plus R by 2, it gives us Q. So that means the minimum element plus the maximum element, their index positions we are saying. Then if it is 0 plus 9 divided by 2, so if see if it is an odd number that comes out, we are going to take the ceiling and then we will divide them into two parts. That is the two sub problems. Then in the two sub problems, what we have one array, we can say, because we have divided the array into two parts. So in the first array, what we have is the array, the index element, the starting point is P and the ending point is q. That is, let us say it is from 0 to 4, and then in the second array what we have, q plus 1 to r. That means the left part of the array. Let us say it is from 1 to 5 and 6 to 10. We have two parts of the array, so the array is divided into two parts. And finally what we have, see, this is the merge sort algorithm. We are calling this function again and again, and every time it is going to divide it into two parts till we get unit element into it. And after that what will happen, once it has been this condition is being satisfied, it will start merging them. So we will see the what is there in the merging step, that we will see in the next slide. So in the merging, what we are doing, we are taking the input array, we are taking the passing the initial position, we are passing the q, that is the division point, how the array is being divided, and r is the last index position. So now we are going to merge the two. In the merge step, we are going to merge two arrays. One array has all the elements from p to q, and another array has all the elements from q plus 1 to r. Now let's make an initial call to the merge sort A. So it starts with A 1 to n. N is the nth element. Now what we are doing over here, you can see this is the function to merge. So now we have two arrays, we are taking n1 and n2. So they are reflecting the size of these arrays. Now for I is equal to 1 to n1, right? So what we are doing, see, we are taking them as the left and the right, because when we are dividing the array, we are taking them as the left part and the right part, and then we are going to combine. So we are going to combine them. So first of all, we take one array which stores the left part of the array, another array which stores the right part of the array. And here you see that how do we come to know? See, we should have certain mechanism in order to find out that now there are no more elements in the array to be combined. So that means what is the end point? That means how do we say this is the last element to combine and nothing is left? For that sake, what is being given is these infinite values are being stored. So whenever we get, see, whenever we have an infinite value, nothing can be greater than that, right? So in that case, we call these infinite values as the sentinels over here, right? The sentinels, you can say they are a kind of flags that indicate there are no more you can say no more numbers to be combined together. So when we are combining, so we have taken the left array, we have taken the right array, and in their last positions we have indicated that the maximum values are there. So whenever we come across the maximum values, that means there are no more values lesser than this, so we cannot combine any more values. That means the merging process is over. So for k is equal to p to r, what do we do? If left L of I is less than R or J, that means we are comparing the corresponding values of the different two arrays. So if L of I is less than RJ, what do? We put A of k is equal to L of I. We require multiple, you can say multiple variables in order to store the values, right? So one variable will you can say navigate through the left array, another variable will help us in navigating through the right array, third variable will help us in navigating to the main array where we are storing the data, so the sorted elements. So then we have A of k is equal to L of I. So since the L of I is already being stored in the A of k, so the index position of I is increased to 1. That means now L of I is shifted to L of I plus 1. Similarly, in the opposite case, that means if L of I is not less than equal to Rj, then we will be storing the Rj into AK. So this is the basic, the insertion, the merging process. We are putting the values of the left and the right subarray into the main array that we want the sorted. So this is how it will proceed, and this is going to take n steps, and its complexity comes out to be of the order of n. So this is the order of n for the merging process only, because when we are merging, so how many elements we are going to merge? We have n elements, so we are going to merge only the n elements. So its complexity turns out to be of the order of n at max. So as I've told you, sentinels, they are used to avoid the check if whether the subarray is fully copied at each step or not. So in order to just verify whenever we come across the infinite, so that means it is fully copied. There are no more elements in that particular array. So the complexity of this function only, I'm saying the merge function is of the order of n. Then in the merge sort, we have seen various steps. So first of all, we have made one comparison which is of the order of on. See, in the merge sort, when we are dividing the array, so it is occurring tn by 2. The second part is also being executed because every time we are dividing it into sub problems at every stage, so it is again tn by 2. And the merge, we have already seen, it is going to be of the order of on because at max we have n elements that we want to merge. So when we see the overall time complexity of this merge sort function, it can be represented using the recurrence relation that is equivalent to 2 into tn by 2, because here we have tn by 2 the merge sort, because we are dividing into left and right two subarrays. So we multiply it by 2 plus theta n plus theta of 1. So when we combine together, so using this equation, we have solved it many times using during the asymptotic analysis, and you can also apply any of the method to solve this equation and you will be able to get this complexity. It comes out to be of the order of theta n log base 2 n. So the best case, worst case and average case, all these complexities of this particular merge sort algorithm is of the order of n log base 2 n, which is lesser than the various algorithms that we have studied, whether you call it the insertion sort, bubble sort, or the selection sort. So the divide and conquer strategy, it helps in getting us a better algorithm for sorting the data. So that means we can apply the merge sort algorithm for large size data as compared to, this is more appropriate for the large size data as compared to the other algorithms. So next we have another one more algorithm that is based, again this is also based on the divide and conquer strategy, but here the divide and conquer strategy is a bit different, as we discussed earlier also in the various kinds of recurrence relations, that these divide and conquer strategy, they have their own ways. So here you can say in the merge sort algorithm, we were dividing the array into two parts. Directly we were just taking the size of the array and breaking it into two parts, divide by 2. But here, what do we do in the quicksort algorithm? In the quicksort algorithm, we pick up one key value, right? So you can say we are picking one key value and then we are dividing that the whole array on the basis of this key value. So we pick up one key value, that maybe you can say we can pick up the key value from the beginning, or we can pick up any the maximum value as a pivot, or we can use any of the pivot values. So you can say the first or the last, whatever array is given to you. So you can pick up the first element of the array and use it as a pivot, or you can use the last element of the array and use it as a pivot. That is basically the key on the basis of which we will be dividing the array into two parts. So what do we do? So on the left side of the array, we take up all the elements which are lesser than the pivot, and on the right hand side of the array, we take all the elements which are greater than that of the pivot. And then we keep on repeating, we apply these two steps on the sub arrays until it becomes sorted. So again, on the basis of these, you can see this concept, how do we write the code for that? So here you can say, given a pivot, partition the elements of the array such that, as this I have already told you, one sub array that contains elements greater than the pivot, and the second sub array which contains elements less than the pivot. So we what do? We sub array is stored in the original data array only. That means all the elements. So we are doing it virtually. So we are just creating an you can say we are putting all the elements. Let us say we have one array and we put that element, the pivot in the center, and all the elements on the which are lesser than that on the left hand side, and all the elements which are greater than that on the right hand side. So we partition the loop, swapping the elements below and above the pivot. So how do we write that? So we have a quicksort function. Now if p is less than r in q, q is equal to, see here the difference. In the previous algorithm, that is merge sort, q was equal to n p plus r by 2. So that means we were simply adding and dividing by 2 and finding out the point of partition. But here we have a partition techniques, because in the partition technique we are going to pick up the pivot and then we will be creating the sub problems, that is the division, divide and conquer. And then we apply the quick sort function repeatedly, and here you can say we have taken the first part of the array and the second part of the array, and any number of elements may be there into that. So here you can see the partition, because it is going to divide the all elements on the basis of pivot, and we are going to do it only for the n elements, and its complexity comes out to be of the order of n. Then for the first array, it comes out to be t of 1, and then for the last one, it comes out to be t of n minus 1. So what do we do in the partition? This is the code for the partition. Here you can see we have pivot. So let us say it's selecting the last element. In this case, we have selected the last element as the pivot. So we take another index of the smaller element, and then we just iterate over it. So integer j is equal to low, j less than equal to high, j plus plus 1. If the current element is smaller than equal to the pivot, so see here, this is the code only for the partitioning. So if the array j is less than equal to pivot, I plus 1 increment the index value of the smaller element, and then we are just swapping so that the you can say the all the array is partitioned into two parts. One on the one side we have the smaller values, and on the other hand we have the larger values, and this keeps on repeating, and finally we are able to get the sorted array using this strategy. So now when we do the running time analysis, so basically the advantage of this sorting technique is that we can sort in place, that is without the need for a temporary buffer. So in the previous case, in the merge sort, we required the temporary buffers, temporary arrays. So because we had to use the merging, and for before merging we had to store the left two sub arrays for and we require the temporary storage for that. But here in this case, as we have already discussed, that all the data on the left hand side of the greater than and smaller than the pivot, it is being stored in the same original array. So we don't require an extra buffer for that. So here we see that the partitioning step, again it has a time complexity of the order of n, and in the quick sort involving the partitioning and two recursive calls, so what we have is t of n is equal to on plus ti plus tn minus 1, and this is of the order of cn plus t of I plus t of n minus 1, where I is the size of the first subblock after partitioning. So now we'll take that if t of 0 is equal to t of 1, so you can say we can consider it as the initial conditions. So to find out the solution for this relation, we can consider three cases. One is the worst case, second is best case, and third is the average case. And all the above cases, they depend upon the value of the pivot. So what is the value of the pivot? So let us discuss that. So in the worst case, let us say the data is already sorted. So what will happen when the pivot is the smallest element or the largest element at the partitioning on a block of size n? The result will yield one empty subblock and one element in the correct place and one subblock of size n minus 1. Because when all the, so if we have taken the largest or the smallest pivot, so in that case what will happen, let us say, because we are picking the pivot at random, either we are taking the first element as a pivot or we are taking the last element of the pivot, and it may happen that the first or the last element whatever we have picked up, that is the largest or the smallest element. So if it is the largest element, then the all the elements that you can say the right hand subarray will be empty. If it is the smallest element, then the left hand subarray will be empty, because we are putting the elements into the subarrays which left hand side, all the elements lesser than the pivot, and all the elements on the right side are the greater than that. And if we have the extreme conditions, in that case one subarray will be empty. So it's going to take on times. So the recurrence relation, it becomes t of 1 is equal to 1 and t of n is equal to n minus 1 plus cn. So the you can say when we solve this, so we get the time complexity of this function to be the on square, which becomes worse than the merge sort, because in the merge sort it's all the time complexities of the order of O(n) log n. Then the running time complexity, let's say in the best case. So you can see this analysis of the worst, best, and worst case, best case, and average case. They are dependent upon the pivot that is being chosen, right? So when we are choosing the pivot, we are not aware whether it is a maximum element or the minimum element. So the pivot is in the middle, let us say, at each partition step. After each partitioning, we have two subarrays which are approximately of the same size. That means like we do in the merge sort, right? So here you can say we take n comparisons, and the recurrence relation becomes T of n is equal to 2t n by 2 plus cn, which is same as that of the merge sort. So that means in the best case, it behaves like that of the merge sort algorithm. The pivot we have chosen, that is the middle element, as it happened as we do in the merge sort. And in the average case, the input would be any randomly generated arrays, and the pivot is at the random position in every step. So it turns out that the average case running time is also of the order of O(n) log n. And we can say that in the average case and in the best case, the performance of this particular algorithm is same as that of the merge sort algorithm. But in the worst case, merge sort algorithm performs better than that of this algorithm. So on the basis of you can say the various studies that we have done on the basis of time complexity, we can compare. Here we can see that the bubble sort, selection sort, and insertion sort, they have the same worst case time complexities, and in the best case, your bubble sort and insertion sort, they are better than that of the selection sort. And the two divide and conquer strategies that we have studied, among these, here we can say the merge sort is better than that of the uh, quick sort in case of worst and best time complexities. But in case of the space over, you can say, here we can see the space overhead is more in case of merge sort, because we require extra buffer for the merging step, but we don't require any extra step for the merging step over here in case of quick sort, because we are storing the data in the original array itself. So when we are trying to solve certain problem, you have to do the analysis, and you have to see what is more important. If you have less space, then you go for the quick sort algorithm. If you have more space and there is no constraint on the space that is required, you can go for the merge sort algorithm for the sorting.